Hey, I'm Mitchell. Welcome to another video in the RSP Education series. Picture this, your motor's spinning slow, but suddenly it's weak, hot, and barely moving your load. What gives? In the world of industrial automation, torque is king, and controlling it at low speeds is no easy feat. From volts per hertz tuning in VFDs to real-time torque correction in servo motors, we're breaking down how a modern system stays strong under pressure. Whether you're dealing with dynamic loads, high inertia, or precision motion, understanding torque control could be the edge your system needs. If you like this kind of content and want more educational videos, please like and subscribe. Also, this video is for educational purposes only. Consult a professional for your application. RSP Supply is not liable for any misuse of this information. With that said, let's get into it. So let's talk now how VFDs adjust voltage and frequency to maintain torque at low speeds. Variable frequency drives, they control motor speed by adjusting both frequency and voltage. But here's the catch. When you lower the frequency to slow the motor down, you also need to reduce the voltage. Otherwise, you risk saturating the motor's magnetic core, which causes overheating. To maintain torque at low speeds, VFDs apply something called volts per hertz control. Basically, they reduce the voltage in proportion to frequency in order to keep the motor's magnetic field strong and stable. However, torque can still drop off at very low speeds because there's not enough voltage to produce full flux. Some VFDs fix this with torque boost or sensorless vector control, which estimates motor load and adjusts output to maintain torque even at low RPMs. Bottom line, VFDs are great at controlling torque down to a point. Below a certain speed, you may need a different control strategy like vector or servo control to maintain performance. Let's talk servo motors. This is where you're getting precision torque control for robotics or CNC machines. Servo motors, they're precision experts. Unlike regular induction motors controlled by VFDs, servos use feedback, usually from an encoder, to precisely control position, speed, and especially torque. In robotics and CNC, you need fast and accurate control of movement and force. Servo systems, they constantly monitor motor torque and adjust it in real time to match the command input. This allows smoother motion with exact positioning, tight synchronization through multi-axis systems, rapid acceleration and deceleration without losing control. Bottom line, servo systems, they're ideal when you need tight torque regulation and accuracy, especially in dynamic or precision applications. Let's talk dynamic loads and inertia. Reflected inertia, gearbox sizing, and acceleration torque calculations. So let's say your motor's spinning a load through a gearbox. The load's inertia, or its resistance to changes in speed, doesn't just go away, it gets reflected back to the motor shaft. So the ratio of the gearbox directly affects how much inertia the motor sees. So for you technical folks out there, reflected inertia equals load inertia divided by gear ratio squared. So if you gear down, the motor sees less inertia. Makes it easier to start or stop. But gearing up, and it's like trying to push a heavy boulder, it'll need more torque and time to accelerate. So when sizing a motor or gearbox, you need to consider inertia matching. So if motor and load inertia are mismatched by too much, it's going to cause instability or overshooting. With acceleration torque, to move a high inertia load quickly, you're going to need extra torque beyond what's needed just to overcome friction. Bottom line, reflected inertia through gear ratios affects how much torque the motor needs for fast and smooth acceleration. Gearboxes aren't just speed changers, they're inertia managers also. Now, how power factor and efficiency losses blend in. So why high torque, low RPM motors may draw more current? High torque at low speed equals high current demand. That's because power equals torque times RPMs or speed, and you're reducing RPMs or speed. So to maintain the same torque, the motor has to draw more amps. Also, when motors run at low speeds, especially with high torque, they operate at a lower power factor. This means they draw more apparent power, even if the real work, watts, stays the same. Lower power factor and higher current equals more heat, more voltage drop, and lower efficiency in your system. Bottom line, when motors push hard at low speeds, they suck up more current and get less efficient. That's why proper sizing, cooling, and VFD tuning matter. So what did we learn? VFDs smartly balance voltage and frequency to hold torque until physics pushes back. Servo systems, they go a step further by using feedback to dominate torque in fast-paced, high-accuracy applications. And let's not forget inertia. It's a silent force that can derail your system if not managed with gear ratios and torque planning. Finally, the price of power at low speeds: higher current, lower efficiency, and greater heat. Bottom line, torque control isn't one size fits all. It's a strategy. Master it and you master the motor. For hundreds of thousands of other industrial automation products, go to our website at rspsupply.com, the internet's top source for industrial hardware.